Let us start our lecture on soil dynamics. We are continuing with our module 5, that is machine foundations. In the previous lecture, we had solved two problems, one for vertical mode of vibration, another for sliding or horizontal mode of vibration, how to design machine foundation. Rather than I should say design, it was basically a foundation size was given to us, also the dynamic loads etcetera were provided to us. It was a cross check type of problem or proof check type of problem, where the displacement amplitude has to be cross checked with respect to the permissible limits. As per the permissible displacement guideline, also as per the qualitative assessment, that is as per Richart's chart. So, continue with similar type of problem using mass spring dashpot model. What we had discussed in the previous lecture, a quick recap of that. We had discussed about yawing mode of vibration using mass spring dashpot model or MSD model, and the equation to compute the natural frequency of the system, also the amplitude of maximum rotation in case of yawing. Then we had solved this problem for both vertical and sliding mode of vibration. We have computed displacement amplitude both at resonance condition as well as at operating frequency condition for two different types of foundation, that is constant force type and rotating mass type excitations, with three different types of soil having G values like this. So, now let us go for rotating mass type excitation. This is for constant force type excitation we had completed. For rotating mass type excitation, what is the expression for A x? To compute the value of A x, that is given by m E E by m omega by omega n whole square by root over 1 minus omega by omega n whole square whole that square plus 2 eta omega by omega n whole square. This is again from our module 2 vibration theory, we get this expression. Basically, it remains same with the vertical mode of vibration also, only changes are wherever the natural frequency etcetera has been changed. And this mass disbalance is creating the horizontal type of vibration, that is another important point to be noted. Means though we have kept in the problem the amplitude of load same, that means for vertical mode of vibration it is acting vertically, whereas for horizontal or sliding mode of vibration it is acting horizontally. So, that is the only change. Okay. So, for A x at G equals to 50, first type of soil, m E E by m we had considered already, calculated as how much? 0.01 centimeter, right. Omega is 157.08 and omega n for G equals to 20 we got 120.62 whole square root over 1 minus 157.08 by 120.62 whole square, that square plus 2.25 times 157.08 by 120.62, that whole square. So much of centimeter if we calculate this in terms of millimeter, it comes out to be 0.178 millimeter, which is less than our permissible limit of 0.2 millimeter. Therefore, the design is okay. And once again, as I have mentioned for vertical case, here also Ax value remains same in both constant force type and rotating mass type, provided the exciting load remains same in both the cases. As it is the case here also, we need not to calculate always like this. We can just simply say that as the exciting load is same in both the cases, the displacement amplitude at operating frequency will be same. Hence, for other two cases, that is with Ax at g equals to 100 TSF will be same as the previous case, 175 millimeter less than 0.2 millimeter, therefore, okay. And Ax for g equals to 200 TSF is 0.064 millimeter, which is less than 0.2 millimeter. Therefore, the design is okay. This is at operating frequency. Now, the same exercise we can do for resonant frequency condition also. And for that, we have seen for rotating mass type, the expression for displacement amplitude at resonance is given by m e e by m divided by 2 eta root over 1 minus eta square. So, it is remains independent of soil type. So, this will give us a single value irrespective of 3 types of soil. So, if we put the values, how much we are getting? So much of millimeter, which is again greater than 0.2 millimeter. Therefore, not okay. The design is not okay at resonance condition. So, when you are checking any design as a consultant in the design office, as a design engineer, you should check both the conditions as I have mentioned, both at operating frequency, that must be always less than the permissible limit, also at resonance frequency, preferably that also should be within the permissible limit. Then you are safe and ensured that your machine foundation is never going to exceed the permissible displacement, and it is safe throughout, whether machine is picking up the speed or starting from 0 and then slowly building up the RPM or something like that, but still your machine foundation will remain safe. So, these are the checks needs to be done, and that can be easily done by using the simple mass spring dashpot model, what we had learned in our module 2 also in vibration theory. So, both no resonance criteria as well as the displacement criteria, and also remember all this displacement calculated you can cross check using your Richart's chart for a qualitative assessment. So, you can check in which zone these points are lying. Suppose if you refer back to the Richart's chart, at this case our operating frequency is 1500 RPM. So, in x axis you go for 1500 RPM, then you have already computed suppose Az, the vertical displacement in millimeter unit, and whatever Richart's chart is given in the corresponding FPS unit you have to convert it. Then in the y axis you find out that value. You can match these two values and find out which point it is coming, and that point is located in which zone. That is, whether it is not noticeable to persons or very severe to persons, in which zone it is lying. Based on that, you can again make another comment based on this qualitative assessment based on Richart's chart. So, that also needs to be checked as well as commented in the design report. So, with this we will continue further with our different models in the next lecture. Now, today let us solve another similar problem, that is by using mass spring dashpot model, find the displacement amplitudes at resonance condition, also at operating frequency of 1500 RPM for rocking and then yawing modes of vibration for a block type machine foundation with plan dimension of 75 centimeter by 90 centimeter and height of 15 centimeter. It is given to us that the external dynamic load or dynamic moment amplitude is given as 1414.8 kg centimeter. Of course, this is kg force centimeter. Consider damping ratio or damping coefficient is 25%, Poisson's ratio is 0.25. Again, for 3 types of soil with G value as 50 kg per centimeter square, 100 kg per centimeter square and 200 kg per centimeter square, we have to obtain this displacement amplitudes for both constant force type as well as rotating mass type excitations. And for rotating mass type excitation, it is given that eccentricity and eccentric weight are given to us, whereas the total weight of machine plus foundation system is 750 kg force is provided to us. So, let us start with rocking mode of vibration, solving the problem. In rocking mode, we have to find out the equivalent radius of a circular base. In this case, the R naught is not like previous equation, that is root over a by pi, not like that. Why? In the previous case, for vertical or horizontal mode of vibration, let me show you here. When a block type machine foundation is subjected to a vertical mode of vibration, in that case what we did, this plan area we had considered, and to find out equivalent radius R naught equation we had used root over a by pi, where a is area of this plan area in the case of vertical vibration, that is the projected area. Whereas, in case of rocking mode, this equation cannot be used. This was for vertical mode. In case of rocking mode, it is going to rock about say center line of this axis. So, we have to find out equivalent radius by equating not the area, but area moment of inertia for a rectangular footing with a circular footing. Is that clear? So, in this case, what we are finding out, the R naught should be by equating the area moment of inertia. So, the formula gives us 16 a b cube by 3 pi, where this dimension is 2a, this dimension is 2b. In that case, this is the formula which will equate the moment of inertia for a circular footing with respect to a rectangular footing. So, in this case, R naught will be 4th root of 16, 75 by 2 and 90 by 2 whole cube by 3 pi. So much of centimeter, because this 75 centimeter and 90 centimeter are the total dimensions in x and y direction. So, for rocking this will be the equation, whereas for pitching it will be a cube b. So, if you compute this, how much we are getting R naught? R naught is coming as 49.08 centimeter. So, check with our yesterday's or previous lectures calculation, what we got in our previous lecture. R naught for vertical and horizontal mode of vibration, it came about how much? 46 point something. It was 46.35 centimeter. 46.35 centimeter was the equivalent radius of a circular footing for the case of vertical and horizontal mode of vibration, whereas for rocking mode it has changed to 49 centimeter. So, we have to remember this expression, and how we are obtaining that also I have explained just now. And from theory of elasticity, to obtain the expression for k, let us denote it as k psi as for rocking. Earlier we have mentioned k psi for yawing. So, now I am changing the symbol. So, it is just the change of symbol, nothing else, but still we are discussing the rocking, because in Richart's book, where we are finally checking the dimensions, there k psi is used as a rocking symbol. It does not matter, it is just the matter of symbol. So, for the case of rocking mode of vibration, k psi can be computed using this expression 8 g r naught cube 3 times 1 minus mu. This is again obtained using theory of elasticity given in Timoshenko and Goodyear. So, in this case g is shear modulus of the soil, r naught is equivalent radius of circular footing, mu is Poisson's ratio. So, now for 3 types of soil, let us find out k psi for this 50 TSF, how much we are getting? 8 into 50 into R naught, just now we have computed 49.08 divided by 3 into 1 minus Poisson's ratio is given us 0.25. So much of what should be the unit? Unit is kg centimeter. Unlike earlier, the unit of k was kg per centimeter, because that was linear spring, whereas these are rotational spring. Okay. So, note it that the unit has changed now, because these are rotational spring constant, not the translational spring constant. So, how much we are getting for this first type of soil? 21017988. So much of kg centimeter. Fine. For other 2 types of soil, g equals to 100, it will be again linearly related with respect to g when r naught and mu remain same. So, just double of this 4203597 kg centimeter, and k psi for g equals to 200 will be double of this, which is 840,71951 kg centimeter. Okay. Now, what is the mass moment of inertia, that we need to find out? M psi we need to find out. to obtain the natural frequency of the system. Now, m psi can be calculated mass moment of inertia using this expression pi r naught square h times gamma by g times r naught square by 4 plus h square by 3. What are different components? Let me explain to you. R naught already we have mentioned, this is the equivalent radius of the circular footing. H is the height of the footing, which is 15 centimeter given to us. Gamma is unit weight of the soil, g is acceleration due to gravity. So, this is basically will come the density, and R naught is already defined, H is also already defined. In this case, what we do not know, gamma value we do not have with us, right. So, we have to assume some suitable value of gamma corresponding to different types of soil. So, let us assume for g equals to 50 kg per centimeter square, first type of soil, gamma is 1.7 into 10 to the power minus 3 kg per centimeter cube. Remember, this kg is kg force, that is why it is unit weight we are considering. For second type of soil, g equals to 100 kg per centimeter square, let us assume gamma as 1.8 into 10 to the power minus 3 kg per centimeter cube, and for g equals to 200 kg per centimeter square, the gamma value is 2 into 10 to the power minus 3 kg per centimeter cube. These are based on how we have assumed this gamma value, reasonable value we need to assume. As g increases, we know it is a stiffer soil. So, that is why we are using standard unit weight of soil in increasing order as the g increases. Okay. So, with this, now let us go back to this equation to compute the mass moment of inertia. So, m psi for g equals to 50 should be how much? Let us put the value pi r, we have calculated 49.08 whole square, then h is 15 centimeter given to us, gamma is 1.7 into 10 to the power minus 3 in kg force per centimeter cube unit. We have to divide it by g in centimeter per second square unit, which is 981 times r naught 49.08 whole square by 4 plus h is 15 square by 3. Okay. And what is the unit? If you put all the units, you will get, it will give us kg centimeter second square. Now, let us calculate this expression and see how much we are getting. 133.215 kg centimeter second square. So, that is for first type of soil. Now, similarly, let us find out for other two types of soil the mass moment of inertia. M psi for g equals to 100 will be, in this expression what are the changes now we should make? R remains same, H remains same, gamma changes as the G changes. So, it will be now 1.8, rest of the thing all remains same. So, only change is in the value of gamma 141.052. Okay. And for third type of soil with G equals to 200, again the change will be only in gamma value 156.724 kg centimeter second square. Why we have calculated these values? Because we know the natural frequency of the system omega n psi should be equals to root over k psi by m psi. Am I right? That rotational spring constant divided by mass moment of inertia. Therefore, let us compute omega n psi for, let us compute omega n psi for first type of soil, that is G equals to 50. That will be k psi, how much we had calculated? 2101798 divided by m psi, how much we got? 133.215. So, if we calculate this, we are getting 397.21 cycles per second. Correct? 397. Okay. Then omega n psi for G equals to 100, the next type of soil, how much we are getting? This value will be double and this one will become now 141.052. By putting those values, we are getting 545.91 CPS. And omega n psi for third type of soil G equals to 200, this will become 4 times and this value will now be 156.724 as we have calculated. So, how much it is coming? 732.42 CPS. So, these are the natural frequencies of the system. And what are the values given to us? Given that T naught psi is 1414.8 kg centimeter, kg force centimeter of course, the amount of moment, amplitude of moment externally applied, and what is operating frequency omega, we have calculated in the previous problem also, it will remain same for 1500 RPM, it is 157.08 CPS, right. Now, let us do the calculation for both constant force type and rotating mass type. So, for constant force type excitation, what is the expression for A psi, that is the amplitude of rotational displacement, is equals to T naught psi by k psi divided by root over 1 minus omega by omega n psi whole square, that square plus 2 eta omega by omega n psi whole square. So, this is the expression as we had obtained earlier also in our module 2, that is vibration theory. Okay. The expression for displacement amplitude remains similar, only the type of forces etcetera changes. And in this case, this is moment by the rotational spring constant. So, whatever value we will get, that will be guided by this expression. Here it will come in which unit? Radian. So much of radian, because it is a rotational displacement amplitude. Okay. So, for first type of soil, that is A psi with G equals to 50, should be how much? This value is 1414.8 by K psi is 2101.7988 divided by root over so much of radian 1 minus omega is how much? 157.08 by omega n psi for G equals to 50, we obtained as 397.21 whole square, that square plus 2 into damping ratio is 0.25 times 157.08 by 397.21, that whole square. All the values where from we got this. Now, let us calculate this, how much we are getting. So, it is coming about 7.769 into 10 to the power minus 5 radian. Okay. And when we need to check this value, as we have mentioned, how this rocking mode of vibration, the displacement is going to take place. If we try to look at the picture, the block type of machine foundation is something like this. About this point, it is going to be rotated by this angle. If we say psi is the rocking angle, about this point O, it was rocking, right. That is what we had seen earlier also in the picture. Let us look at the slide here, so that it will be clear to us once again. Look at here. So, for rocking mode of vibration, it is rocking about its base. So, this much is the maximum amplitude. So, how much is the linear displacement is going to occur? You can multiply it with respect to the height of the foundation. That will give you how much is this displacement is going to occur in this direction. Okay. That needs to be checked with respect to our 0.2 millimeter, or not or and with respect to the Richart's chart for qualitative assessment. So, remember that. So, let us find out the other two cases for how much is A psi we are getting. Similarly, in the previous expression, what are the changes now will occur? Let us see. This T naught psi remains same, K psi changes as the soil changes to 100, this will become double. Omega remains same, whereas omega n psi change to 545.91. Here also eta remains same, omega remains same, omega n psi changes to 545.91. So, by putting those values, how much we are getting for A psi 3.625 into 10 to the power minus 5 so much of radian. Also for the third type of soil with G equals to 200, if we put the corresponding value of k psi and omega n psi for third type of soil G equals to 200 kg per centimeter square, we will get 0.753 into 10 to the power minus 5 so much of radian. Okay. So, these displacement what we have computed, those are at operating frequency. Now, we need to find out the displacement amplitude at resonance frequency also. So, at resonance frequency, based on the expression of DMF, we can find out how much is A psi R, means at resonance. The expression for that will be T naught psi by k psi by 2 eta root over 1 minus eta square. That is the expression from DMF we got. Again, it will be guided by this unit, which will give us radian. Fine. So, let us compute it. A psi R for 3 different types of soil. For G equals to 50 kg per centimeter square, it will be 1414.8 by 21017988 divided by 2 into eta is 0.25 root over 1 minus 0.25 whole square. So much of radian. If we calculate this, how much we are getting? 1.39 into 10 to the power minus 4 radian. Okay. And for other two cases, at G equals to 100, the changes will be, this remains same, k psi will become double, this remains same. So, it is basically linearly will decrease by half from this value. So, it will be 6.952 into 10 to the power minus 5 radian, and A psi at resonance for G equals to 200 kg per centimeter square will be half of this again, 3.476 into 10 to the power minus 5 radian. And one observation which you must have noticed, the values of A psi R will always be greater than the values of A psi, which is quite obvious. That is, displacement amplitude at operating frequency will be less than the displacement amplitude at resonance. So, this is a kind of cross check you can do. You can check whether the obtained or calculated values are really for resonance condition are bigger than the operating frequency or not. If it is not, then probably some calculation mistake somewhere we have done. So, for a design or a design check, this way we have to carry out the calculations. So, this completes the rocking mode of vibration case. Now, let us move to next case, that is this yawing mode of vibration. Let us come to now the rotating mass type excitation. We have calculated only for the constant force type excitation. So, for rocking mode, we have to now do the calculation for rotating mass type excitation. For rotating mass type excitation, what is the expression for A psi? That is m e e z by m psi times omega by omega n psi whole square by root over 1 minus omega by omega n psi whole square, that square plus 2 eta omega by omega n psi whole square. This is the expression to get the displacement amplitude, rotational displacement amplitude for rocking mode in case of rotating mass type excitation. These are well understood. Where from this has come, this expression? You can equate it with respect to, in case of vertical and sliding mode, it was m e e by m, that is eccentric mass, eccentricity divided by mass of the total system. In this case, it will change to equivalent moment, because now it is the rocking displacement or rocking mode of vibration. So, the external load which is applied on the system has to be a moment. So, how much is the moment applied because of the eccentricity, that is m e e and z? How much is z? Z we can consider with respect to C g, how much it has displaced. So, in that case z will be half of the height of the foundation. Okay. So, that is a standard assumption. We can take z as the h by 2, that is with respect to center of gravity of the system. If we consider the eccentric mass is creating this much of moment with respect to its C g, and m psi already we have calculated, that is mass moment of inertia. So, instead of mass, now mass moment of inertia has to be considered here. Again, the unit of this will be guided by this unit, which will come as radian. So, for the first type of soil, A psi for g equals to 50 kg per centimeter square, how the calculation will be done? 75, then 0.1, then 7.5 is h by 2 divided by 981 into m psi, how much we got for g equals to 50 kg per centimeter square, 133.215. Where from this 981 has come? This was eccentric weight is given to us. If you go back and look at the problem statement, look at the slide. Here eccentric weight is 75 kg. As I have said, weight means kg force. So, to find out eccentric mass, we need to divide it by g. So, that is why we have divided it by 981 here. Omega is how much? 157.08 operating frequency, and omega n psi for g equals to 50 we had already calculated 397.21, that square. Now, divided by root over 1 minus 157.08 by 397.21 whole square, whole that square, times 2 into 0.25 into omega is 157.08, omega n psi 397.21 whole square. So much of radian. Now, let us calculate this, how much it is coming. It is coming 7.769 into 10 to the power minus 5 radian. Again, the observation is that in rotating mass type case also we got at operating frequency, the rotational displacement is same as the constant force type, provided the externally applied moment is same in both the cases. So, if you calculate this, how much external force is getting generated, how you will calculate? Q naught was MEE omega square, that has to be multiplied with respect to the lever arm, you will get the moment. Is that fine? Now, let us calculate for other two cases of soil, A psi for g equals to 100. What are the changes? Let us look here. These values will remain same, only m psi will change as the soil type changes. Also this omega remains same, but omega n psi will change as the soil changes. So, by putting the corresponding value, we should get the same displacement as we have obtained for the constant force type case. And A psi for g equals to 200 is coming 1.753 into 10 to the power minus 5 radian. Now, let us find out how much is A psi r, that is at resonance condition, how much is the rotational displacement amplitude, that is computed by using this expression m e e z by m psi divided by 2 eta root over 1 minus eta square. This is the expression, once again we are getting from the expression of DMF. So, A psi r for g equals to 50 will be 75 into 0.1 into 7.5 by 981 into 133.215 divided by 2.25 root over 1 minus 0.25 square. So much of radian. If you calculate this, we are getting 8.89 into 10 to the power minus 4 radian, which is obviously larger than at operating frequency how much we got A psi, which is 7.769 into 10 to the power minus 5 radian. Now, let us compute for other two cases of soil, that is G 100. The changes will be only at this value of m psi will change, all other things remain same. So, by calculating we are getting 8.4 into 10 to the power minus 4 radian, and A psi r for g equals to 200, we are getting 7.56 into 10 to the power minus 4 radian. So, with this we are now actually completing this rocking mode of vibration results. For rocking mode of vibration, what are the displacement amplitude both at resonance condition and at operating frequency for constant force type and rotating mass type excitation with 3 different types of soil. So, with this we will stop our lecture today here. We will continue further in our next lecture.